Welcome, guys. Yeah, so previously we have proved the class equation and talking about the class equation. Yeah, so in this video, let's prove the previous. There's a theorem that we prove for the abelian case, of which we want to prove non-abelian. Okay, so Cauchy, this theorem is important. So P is prime, and P divides G. So basically, you have some finite group, which P is a divisor. P divides the order. Then G has an element of order P. Okay, so basically, you can find element X belongs to G such that XP is identity. Okay, and I think we prove. I think I proved this. So I proved the abelian version. So I proved the. I proved that when G is abelian, this is true. Okay, so this is due to using a homomorphism idea. Okay, so I think probably it's in the group homomorphism part. Okay, but I think it's in the group homomorphism part. Okay, so this theorem, Cauchy theorem for abelian group. This also CO theorem for abelian group. So it's a very complicated proof. Okay, but in this video, we hope to prove non-abelian. Okay, so from class equation. Okay, so remember that we define a center. Basically, it's all the group elements such that they commute with everything. Or Y belongs to G, and then we also prove the normalizer, normalizer of A, which is a thing which commute with A, right? So it's Y equals to YA. Okay, and the class equation tell me that G is the same as Z, so the order of Z plus the element, which is all the normalizer not the same as the whole group, and you take G and let's say n of A. Right, so this is a class equation. Okay, we want to be using this equation to prove. Okay, so assumption is using the induction. Okay, mathematical induction. Okay, so idea is that I hope to find some element which is non-identity and which prime power is identity, right? So I make an induction on something, right? Induction on the group G. Okay, so I assume this is true. So the original theorem is true. I assume Cauchy is true for any group with the order less than G. Okay, yeah, so group of order 1 is trivial, right? Okay, so this is my assumption, right? So if Cauchy, if we can show that this Cauchy works for let's say finite group of G, some subgroup of G, which is W is the proper subgroup. If I can show that this Cauchy theorem works for this, and also P is a device order, then by our induction, right? By our induction, we will find some A belongs to W such that A P equals identity. Okay, so if this works, so the key idea is that if we find some subgroup which satisfy this property, then we already get an answer. So if I try to conversely prove this theorem false, then I can assume no subgroup has order P, no subgroup W such that the P divides W. So basically, I want to claim that such that P divides W. So I want to claim that this is impossible, right? So then conversely, you prove the theorem is true. Okay, so let me say again. So let me say again. So what I'm saying is that if this theorem is, if I want to prove this theorem, I want to prove this Cauchy theorem is true, then I do an induction, right? Okay, but so if I find something that some subgroup which P divides, then by our induction, then we get an answer, right? So if this theorem is true, it's false, then I should be able to that I can find some subgroup which is a W such that P do not divide W. Such that P divides no such subgroup that P divides W. So this is our assumption. Okay, so a particular. So let's say if A not so let's for working our class equation. Right, so we have still be class equation. Okay, so by definition, this P divides this, right? And also we know that if P divides this, and this NA is not the same as G, right? So P will also divide NA, right? Because by our assumption that P should not divide N of A, right? So any subgroup cannot be divisible by P, okay? So which tell you that this is divisible by P and this is divisible by P, right? So which tell you that P divides Z, right? So P divides N2. Okay, but now this is troublemaker, right? So Z cannot be a proper subgroup, right? Because we want to prove that if Z is a proper subgroup, then we use our previous assumption, and then we get a proof, right? So the only case is Z is a whole group, right? But that means the center is a whole group, so G is abelian. So if G is abelian, then our previous theorem works. Okay, works. So whatever is abelian or non-abelian, then this theorem also both works. Okay. Okay, so this is the first part. Proof is done. Okay, so next I want to talk about the conjugate class. So conjugate class. Class in a symmetric group. Okay, so let's just define a so-called partition. Right, so the partition of N is basically you can write N1 plus N2 up to some Nk, right? So K can be whatever, and but N1 need to be less or equal to N3 that's equal to Nk. Okay, and the Pn is the number of partition. Okay, so simple example is P of 1 is just 1, right? There's only one way, so P of 1 is 1. How about P of 2, right? So one can write 2 as a 1 plus 1, right? By the way, this all number must be greater or equal to 1, right? So the only way to write 2 is 1 plus 1, right? You cannot write 2. This is one way, and another is that you just write 2 as 2, right? So P of 2 should be 2. Okay. How about P of 3? So 3 can be written as 3, or 2 plus 1, or 1 plus 1 plus 1, right? So it must, I mean, you can write it's 1 plus 2, right? So basically, it must increasing, not strictly increasing, but also each one must be an positive integer. So P of 3 is 3, and then check of P of 4. P of 4 can be 1 plus 1, 4, and 1 plus 1 plus 1 plus 1. 3 plus 1, 2 plus 2, 2 plus 1 plus 1, right? So you can write dynamic programming if you like the computer science. P of 4 is 5. Okay. So you can simply, this is not easy to prove, but the P of N is very large. So I remember that it's exponential N or something. Okay, so for example, P of 6 is 11, and P of 5 is 7. Okay, don't worry, just some stupid things. Okay. Okay, so I also say that if any element is Sn, there is a cycle permutation, cycle representation of sigma. Okay, so remember that. So for example, this is one example, right? So suppose this is sigma, right? So right. So from here that we can see 1 and 7 are fixed, right? So so one is 1 and 7 are fixed, right? So I can write this 1 and 7. Oh, but in the 2 to 3 are changed, right? So I can write 2, 3. And I see that the 4, 5, 6 are exchanged, right? So I can write it 4, 5, 6, which this means that 4 go to 5, 5 go to 6, 6 go to 4, and also 9, 8 are exchanged. Okay, so this is a so-called cycle. Basically, it's a one cycle representation. Okay, so we see that this forms the partition. Okay, so total length of sigma the total length of sigma is 9, right? So this is 1 plus 1 plus 2 plus 3 plus 2, right? So that means this 1, 1, 2, 2, 3 is a partition. It's a partition of 9, right? It's a partition of 9. Okay, so obviously that since you always have cycle representation, so you can use every sigma. So every element will have some will corresponding to some partition of the right. So every element in Sn will give a partition of n. Okay, so theorem which is we're gonna prove is that if x and y in Sn, which is conjugate. So remember that the conjugate means that you can find the a in Sn such that x equals a, y a inverse, if and only if they have the same partition. Okay, so this is the non-trivial thing. They have the same partition. Okay, and or just say that the conjugate class of the, let's say if you take x belongs to Sn, the conjugate class of Sn, which is n of x, is just a partition of n, which n is the partition of x. Oh, sorry. I'm stupid. So what I'm saying is that the number of conjugate class. So basically, all the how many different classes, right, corresponding to different partition. So P. Okay. So this is our video. So final the goal of the rest of the video just to prove it. Okay, I think this is interesting. Okay, so let's see the reason. Okay, so let's maybe just solving this by a simple lemma. So this lemma tells you that how do you compute theta and sigma in Sn, right? So let's suppose I want to compute this. Okay, so let's assume that theta will map I to j. So theta map I to j. Okay. What about this? Okay, so suppose that theta send I to S and j to t. Okay. Then let's check about this. Right. So okay. So this is my, so you see C. So theta, suppose theta send I to S. Right. And but what about this sigma? So I don't know sigma send it to something or not. So maybe let's see. Maybe let's see how to see this. So yeah, there's a different convention, right? But let's maybe see. So what's the theta inverse, right? So theta inverse will map S to I, right, and T to J. Okay, so I want to claim that this will map S to T. Okay, the reason is that let's maybe write this way. Okay, so I want to claim that these guys send to S to T. The reason is that this theta inverse send S to I, right? So S map to I, and this theta send I to J, right? So I to J, and then this theta say J to T, right? It's send J to T. Okay, so this is S map to T. Okay, so I should write theta sigma theta inverse. Okay, so but the convention is that we start from the right. So okay, because some people times to start from the left, right? But I want to start from the left, right? Okay, so which tell you that theta inverse, should just write it as a if you want to compute this, you just replace every symbol. So you replace every symbol in sigma by its image under theta. Okay, so replace every symbol in sigma by its image under theta. Okay, so this should be simple. Let's see an example. So maybe theta is 1, 2, 3, 4, 5, 4, 7, and this theta is 5, 6, 7, 3, 4, 2. Right, so I can see that right now I want to compute this theta sigma theta inverse. Okay, so the theorem just tell me that replace every symbol in sigma by its image on the theta, right? So, well, where is 5? Right. So in this case, theta does not map 5, right? So 5 still fixed. 5 still fixed, so 5 map to 5, right? How about this 6? So 6 doesn't show this, right? So 6 still survive, so 6. So 6 becomes 6. What about this 7, right? 7 map to 4, so 7 map to 4. And the 3 map to 2, right? So 3 map to 2. What about 4? So 4 map to 7. And the 2 map to 2. Oh, sorry. So what? Sorry, I'm stupid. So 3 map to 1, right? So sorry, it should be this way. So 3 map to 1. And 2 map to 3. Right. So from here you see that you see what? You see 5 by 5, right? 6 by 6. And right, so yeah, this is just okay. So now you can write down your answer. You just replacing this into in terms of this, right? So it become 5 by 5, 5 0 5, 6 0 6, 7 become 4, and 3 become 1, right? And 4 becomes 7, and 2 becomes 3. Okay, you can try by just putting the brute force. Okay, but hopefully this theorem tell you the answer. Okay, so by this algorithm, right? You see, if you times this, then the answer will still be the cycle, right? So this is 3 3 partition. This is 3 3 partition. Okay, so it tell you that the conjugate will not change. Will not change the partition. Will not change the partition. Okay. Okay. And so this also tells the answer that yeah, basically this lemma proves what we want, right? Okay. Let me just rephrase it carefully. So suppose your sigma is, let's say, A1, A2 up to AN1, and B1 up to BN2, and also up to X1, X2, and XNR. Right. Suppose this is your sigma, and your tau is alpha 1 up to alpha n1, right? Same same partition. So it's beta 1 up to beta n2, and also chi 1, chi n2, right? So you can check that. So I want to prove that tau can be changed into sigma, right? So I want to find some smart data which connect these two, because I claim that if they are the same partition, then it must be conjugate itself. Okay, conjugate to each other. Okay, so I can find the theta as right. So this is trivial, right? Because by my rule tell you that I can just replace every A1, right, in terms of alpha 1, right? So the theta just write as A1 alpha 1, A2 alpha 2, AN1 alpha n1, B1 BN2, beta 1 beta n2. Okay, so it's tautological proof. Almost trivial, right? Once you understand these algorithms. Okay. Okay, so let's do an application. So there are two applications I think is very trivial. Okay, so the first application is that so our results tell you the number of conjugate class in Sn is just Pn, right? Partition of n. Okay. So what is the, let's say, so let's using this theorem to answer a question. So what is the conjugate class? Let's see. Okay, so what is the element commutes? So I want to ask about what's element commute with 1, 2, right? So 1 permutation 2, 2 permutation 1. Okay, so obviously that anything, right? Anything do not permute 1, 2 will commute with 1, 2, right? So how many of them, right? So basically it's 3 to n, right? You can literally permute it, right? So there should be n minus 2 factorial, right? And then 1, 2 can change it to, and then 1, 2, at least 1, 2 can be, so 1, 2 square will be identity, right? So so you should times 2, right? Because you can permute this, you get n minus 2 factorial, and you can choose whatever you want to permute. You want to have one permuted, one change to 2, or 2 change to 1, or you just make it identity. Okay, so this is this is naively this is the element that commute with 1, 2, right? So so if I write as a formula, I should say that tau should be anything commute with 1, 2. I believe to be 1 to some power I, and also let's say t do not contains 1, 2, right? So t do not permute 1 or 2. Okay, so this is my and I can be 0, 1, right? So this is my my assumption. And but using this theorem, right, I can prove that this is the answer. Okay, because what? Because the number of, so order of 1, 2, right, by our theorem, this G divided by order of 1, 2 will be the conjugate class of 1, 2. Conjugate class of 1, 2, right? Is it correct? Yeah, the conjugate class of 1, 2, right? So who is conjugate class of 1, 2? It's the number of the, so basically it's the number of 2 partition, right? So how many is the number of conjugate class of 1, 2, right? So the conjugate class 1, 2 means that you can write any a b, right? Because we proved that the same partition will be conjugate, right? So the number of this will be n times n minus 1 divided by 2, right? And this G is n factorial and n 1, 2, right? So which tell you that n 1, 2 will exactly be 2 times n minus 1 factorial, sorry, n minus 2 factorial, right? So that means that we prove that everything commune with 1, 2 has the order of this, right? But we already find everything in this. Okay, so basically we show that everything commune with 1, 2 must be the form of this. Okay, so this is the first application. Okay, so this application say that you can prove that everything commune with 1, 2 must looks like form of this. So T does not commute with 1, 2. Okay. Okay, so application 2. So let's think about application 2. Okay, so application 2 is that in Sn, I want to ask what commutes with 1 to 2 to n, right? So this is the permutation that you 1 to 2, 2 to 3, 3 to 4, and n to 1, right? So what is the guy which commute with it? So ideally, I should say the 1 to 2 to n, right, up to k, right? So the power of this should commute with cell, right, by definition. So k should be 0. So 0 map the identity commute with everything. The 1 to 2 up to n minus 1, right? If you go to n, then everything will just go back. So my belief, so so this is my intuitive, right? So my guess will be n of 1 to 2 to n should at least greater or equal to n, right? Because there are already n animated. Okay, and the theorem tell me that this n factorial divided by this n 1 to 2 to n, this guy should be the conjugate number of conjugate class of, so it's conjugate class of 1 to 2 to n, right? So conjugate class will be the same partition of n. Okay, so this is just the n cycles, the distinct n cycles, or distinct n cycles in Sn. Okay, so this should be high square problem, right? So suppose you only have 2, your distinct cycles you only has. Yeah, so I mean 2, right? Your the distinct cycles. So if you n equals to 2, right? Your distinct cycles you only has 1, right? Because this is only distinct cycle. How about n equals to 3, right? So you get the 1. So this is one cycle, 1 to 3. And then you also got another which is a 3 to 1, which is different cycle, right? So these guys total contains 2, right? So you can easily prove that for general n, which is n minus 1 factorial. Okay. So this is n minus 1 factorial. Okay, so for n factorial might divide by something which is n minus 1 factorial. So n1 to n, just n. So which prove that all the things coming with 1 to k up to the n k, which is here. Okay, so from this you can easily generate to get who is the guy coming with cell in the symmetric group. See you guys next videos. Bye bye.